Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP,
Hello.
where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Good morning, everyone. How are you? Into the last day. Excited? Okay. Full of energy yet? Okay. So let's start today's session. Today's session is like one talk, and then there are some formalities regarding the program, regarding this school. So today is the only speaker, first speaker as well. Professor Malik Maza, who is a senior researcher, nanosciences laboratory, materials research department. We already have like couple of talks, so you are well familiar with him. So with that, let's welcome Professor Malik Maza.
Thank you. Very kind. Okay. Yep. Thank you. Thank you. Thanks a lot. Thank you. Very kind. Can I start? Thank you. First of all, Program Director, dear senior and junior colleagues, thank you again. Allow me please to express my gratitude to the local organizers as well as to the ICTP family by large for their kind invitation in associating us in this endeavor. My talk of today, as you can guess, it's related to nano. You have noticed that Prof. Jarog, when he presented to us his outstanding presentation on attosecond pulses, he investigated extensively the nanowires. And the previous speaker of yesterday who was targeting or sharing with us the modeling aspect, he was speaking extensively on the size of the particles and the regime, in particular controlled by the ratio of the wavelength of the probe relatively to the size of the target. And there were not quite a number of trainings that you have had with the professor and his assistant, whereby you spoke a lot about the meta. You have highlighted quite extensively nanoscale for photonics. So I think it's really important to shed light what to have sure that with your background of this marvelous comprehensive week about photonics. So we'll be going for the aspect of nano. Yes. So the title of my talk today is on the singular properties of at the nanoscale. Yes, thank you. So, more or less the outline of my presentation consists of three major parts. Allow me please to do more or less some, not marketing, but to introduce you to who is the U2ACN2. And then go and share with you the base of nano, the background of nano. Then give you some typical examples, on the nano, but I will go case by case, and these different cases that I would like to share with you are are selected by of the spectrum of a wavelength. So I'll start somehow by the gamma rays and then go to the X-rays. From the X-rays I go to the UV. From the UV I go to the visible, and from the visible I go to the infrared. Just to give you some typical examples to show you that materials at the nanoscale are used as photonics all over the spectrum. In addition to that, you would see that when you embark in nanomaterials or nanosciences or science at the nanoscale, you have to ensure that you have to be sure that either the application of these nanomaterials are in the photonic field or optical field, or that you will be using extensive amount of photonics and optical tools to probe the matter of or the properties of these materials. I will start with one colleague, which, sorry, but I have to introduce you. As I mentioned, I repeat myself, please. I do apologize for those who got it clear in their mind. I want to introduce who is the UNESCO chair. This talk is given within the framework of this U2ACN2. If you do remember, U2 was a fantastic and is a fantastic music group. The music is really perfect. I advise you to listen to it, and therefore you would remember U2ACN2, our chair. And this chair, it's styled, abbreviated U2ACN2. It's related to the UNESCO, UNISA, Africa Chair, Itamba Labs NRF Africa Chair in Nanosciences and Nanotechnology, and it's a trilateral partnership between the UNESCO, Place Fontenoy in Paris, the University of South Africa, UNISA, and Itamba Labs, which is the largest facility of the National Research Foundation, NRF. And NRF is the equivalent of the NSF, but with the smaller budget, of course, as you can guess. The CU has two major nodes, one in what we call the Gauteng province, Pretoria and Johannesburg, and the other node is in the Cape. The bulk one is in the Cape, where Moses and Nancy are based. And by having two nodes of such located at different geographical locations, that gives us the opportunity to access the equipment and the infrastructure of UNISA in different departments. And here we have access to facilities which are proper to accelerators, because here it's an accelerator-based sciences. We see, for example, the case of the gamma rays that I will share with you. Gamma rays and X-rays are at the bottom of the spectrum, the electromagnetic spectrum. Here we have access to such a kind of radiations. And why Africa? It's not a segregation type, no, at all. But the point I'd like just to share with you something, colleagues and fellows. When we speak about nano, is the size. The size matters. Is it big or is it small? And here I would like just to show this image here, which I hope that you would remember it forever, because the Mercator projection of the world map that we do see all over is not correct. It does not reflect the true size of the African continent. Africa is just, it looks like small. And if you take, if you take, for example, the case of Russia, if you go to St. Petersburg, somewhere here, to Kamchatka here, Russia is the largest country in the world. If you go from the Kamchatka to St. Petersburg in the Mercator projection, this distance is higher than this distance, which is wrong and correct. It's the opposite. This distance from the Horn of Africa to Dakar, to Senegal, is higher than that distance. So the Mercator projection was used because it was Eurocentric. Because, Europeans they were the ones who made these maps and so on. But just to give you an idea how big is Africa. Africa, the size of Africa is the size of the USA, the full USA, including Nebraska. In this, if you use these small parts which were not occupied, including Nebraska, plus it's the size of China. It includes the size of China as well as of India, including all Western and Eastern Europe, in addition to the UK and Japan. I hope that you got right here. So, the size of Africa is huge. So when you speak about Africa, you are speaking about continents, not a country. In addition to this, while our focus on Africa, with my great respect to our colleagues from the north, it's not a problem at all, is that Africa is the youngest continent. Africa is the home of 10 youngest countries in the world. And it's the home of the youngest country or nation in the world, that is Niger. There are more youngsters than elders. In addition to that, colleagues, it's a pity that it's not a high resolution here, but anyway, it is more than 73% of the population of Africa is under age of 18 years old. So it's really the youngest continent. And the prediction of the United Nations is that it gives Africa to stay as the youngest continent in the world up to 2100. So it gives you more or less an idea, a perspective, colleagues, that there is a huge, massive of population coming of learners, and therefore the education system has to absorb them and has to educate them, and certainly, God willing, that the next Einstein would come from Africa as well. That is what the target of the Perimeter Institute in Canada and the UK, and also this workforce, colleagues, of these youngsters, they have a mind shift from not only knowledge generation or getting a certificate and a diploma, but to also innovate. I wish just to single out that PayPal, you may think that PayPal was innovated by Elon Musk. No, it's wrong. Give back to Caesar which belongs to Caesar, and to Cleopatra which belongs to Cleopatra. PayPal was patented by Elon Musk, but modified. PayPal was innovated by two engineers from the University of Jomo Kenyatta here in Kenya. So the next Elon Musks must become from this country or from this classroom here. The activities of the UNESCO chair that we are dealing with are nanomaterials for energy, nanophotonics, which is a really singled out thematic, biomimics and green nanochemistry, materials radiation hardness for space applications, and nuclear accelerator based engineered materials. Is it me who is doing this, colleagues, or is it some? Thank you. Thanks a lot. I mess up quite a lot, so I want to be sure that it's not me. Anyway, the UNESCO Africa Chair in Nanosciences and Nanotechnology is a network of excellence of the African Union, and it's the sole, God bless, and it's the sole chair of the UNESCO in the field of nanosciences and nanotechnology in the South. When we applied in 2012, when the UNESCO made the call to create a chair in the South, China, Chinese colleagues, Mexican colleagues, Brazilians, and so on, have applied. And in our case, when we competed, it was the first day where the UNESCO Commission has decided that it has to go to Africa, not because Africa, no, because in effect, UNESCO chair in 2013, we were operating under the framework of what we call the Nano AFNet, the Nanoscience Africa, and ICTP network number 63, and that is why, which was created in effect in Trieste. So the nano idea or the nano concept for Africa was born in Italy, in Trieste, where my colleagues originate. And of course, the major activity of the Nano AFNet and the UNESCO chair are capital development and capital mobility. Human capital is related to the training of MScs and PhDs in multidisciplinary fields of nano, chemistry, physics, life science, computational, engineering, and so on. And as you can see, colleagues, they are from different countries: Burkina Faso, Uganda, I think Ghana, Senegal, South Africa, Egypt, DRC, Botswana, and so on, including previous countries where there was a war, that is Rwanda and Libya. And as you can see, colleagues, that also we have not limited ourselves to postgrads, MScs and PhDs, but also emerging and early career scientists, whereby we have quite a number of fellows from Sudan, Cameroon, Morocco, India, South Africa, Iran, if I single out here, Mahmoud Akbari, Ghana, and so on and so on. and Yemen. And in line with SDG 5, we do believe firmly that the gender equity is a must. I was telling last time to my dear colleague, Professor Alessia, here present, I was telling her that I think we are really, in Africa, we are really neglecting 50% of our GDP. And how can I say, if you compare with the countries in the north, that is Sweden, Denmark, and so on, where women component is very active in the society, well, they do not have the cobalt, they don't have the copper, they don't have what we have, but yet they are so far higher than us. They have not neglected their the female component. And I was just telling to her that in effect, there would be no Christianity if there was no Mary the Virgin. There would be no Jesus. Rational wise. And the first believer in Islam was Khadija radiallahu anha, the first wife of Muhammad Rasulullah sallallahu alaihi wasallam, the Prophet. And the first Muslim was her, and she was a businesswoman, colleagues. She was a businesswoman. And the Prophet was she was his employer. She was the one who employed him. And well, humanity, the man has made it, change it in a way that a male is dominating stuff. No, it's wrong. Who is the most important? Is it the chicken or the egg? No, colleagues. We have to, and we are not comparing who is who, but the point is we need to give the credential to our female colleagues, whatever our thought, whatever our philosophies and religions. And you cannot be a Jew if your mother is not a Jew. So, simply clear. So I think, colleagues, I beg you, you are here, I beg you to be, and for my male colleagues, I beg you and plead to you, each and all, to be the advocate for our sisters and daughters, to ensure that they will contribute to the society. And those colleagues, all these fellows, I must admit, all these fellows got the L'Oréal UNESCO Award for Women in Science. That means they are highly qualified and clever and highly committed. So we cannot neglect this female aspect component. Well, colleagues, all these fellows who have been trained, they go back home. They go back home and they become our alumni. They become advocates to the UNESCO chair. And certainly Moses and Nancy would be our ambassadors here, not only in Kenya, but in the southeast of Africa. And we are increasing our global footprint, of course. The research that in the field of nanosciences and so on, generally speaking, fits and is in line with the Sustainable Development Goals of the UN, and therefore, in our case at least, we obey by that and we try to contribute. Our contribution is a droplet in the ocean. It's small, yes, certainly, but it is a contribution. And colleagues, all these fellows end by getting their diploma from the University of South Africa or sister nations, or a double diploma, one from UNISA, one from the home countries. And how can I say, in particular, this is very sound for the Francophone countries, whereby you have a diploma from an Anglophone system and a Francophone system. And it opens, of course, quite a number of possibilities to the fellow. And as you can see, colleagues, we are not limited only to Africa, but the global south, that is Iran, to the global south, that we are in the footprint on the path of late Abdul Salam somehow. And colleagues, when we operate in this way here, when you bring fellows from different education systems and so on, it happened that we embark in a co-supervision, and therefore we how can I say, we embark in collaboration, not only the co-supervision, but sharing facilities, sharing knowledge and so on. And of course, when we produce, colleagues, there is the publications as you can see, this is the site of the work of the publications published under the framework of these two platforms, in particular the UNESCO chair. As you can see at the beginning where we were operating alone, we were at the bottom here, low, some hundred or some tens of citations. When you, these citations, when you publish a paper, when you produce a publication, and that publication either attracts the interest of the international community or not. If what you have produced interest, they will quote it and they will cite it. So higher is the citation, and these citations are not from Africa, of course. They are from China, New Zealand, the US, name it. And this citation is a reflection of the quality of what you are producing. And as you can see at the beginning, where we were alone, we were producing with our citations, they were low. But when we started to work together and co-supervise students together, exchange, how can I say, use jointly our mutual equipment, and you see within the years it's just rocketing. It's just rocketing, and that reflects the quality of the research that we are producing, and it reflects also the level that we are gearing towards. So it's a good indication. That means what we are doing is of a quality. That does it mean, or that is the meaning of this. And what is extremely important, it came because we do cooperate. We have co-supervisors from Tunisia, students in Tunisia, in South Africa, who said that one day we'll have Francophone countries, Anglophone countries. So we are, how can I say, we transcend the barriers of languages, we transcend the barrier of the location of the institutions and so on. And it's really important for Africa, either we do it or we die. C'est tout. You are obliged to do it. So here we are, and how can I say, our role model is the ICTP system, is the Abdul Salam ICTP system. And colleagues, we are extremely grateful to the Trieste system in general, because they are the ones who believe in us. They are the ones who gave us the seed fund as early as 2004. So whatever we reached is due to these institutions and to the Italian citizens, to whom we are grateful forever. And I will not go through these colleagues. When we embarked in 2005 in the field of nanosciences at the within the African continent, we said that let us start with the nano-human capital development. Let us train MSCs and PhDs in the field of nanosciences. Let's also not neglect senior young and career scientists. So that is more or less the case, and we started from 2005 up to now, non-stop. And we said that by 2020, we should have been able to create a nano master program at the African continent, or at least institution to institution. And we said that by 2020, we should have been able to create a nano journal, which is recognized by, how can I say, the metric institutions such as Scopus, the Web of Science, and so on. And this one also we have succeeded, and this one we have created Nano Horizons jointly under the patronage of the Royal Society of the UK and Open Science International Germany and UNISA Publishing House. So you are more than welcome, please, to submit and to assist us in making this platform a successful one. And we said in 23 we should have produced enough manpower and capabilities both the master and the PhD level, as well as emerging and senior scientists, and therefore we would have accumulated enough knowledge, and we have created quite linkages within Africa itself, including our colleagues from the north, and the case we have colleagues from the University of Milano, the Polytechnic of Milano, we have the ICTP, we have other colleagues from Max Planck Institute last week. So we said that once we have that, we should now think about R&D translations, come with innovation and patent, if possible, and try to, how can I say, translate this into a technology. Well, why nano, colleagues? Why really we have to advocate for nano? Field of photonics, it's multidisciplinary. You find it everywhere. When you brush your teeth, that is a nano that you are using. When you go to and you protect your skin, the cream, that is a nano component, colleagues. And allow me please to justify why. First of all, because it's multidisciplinary, like photonics. You can, how can I say? Yes, indeed, the field of nanosciences and nanotechnology is material-centered, but it has linkages with all disciplines, with really all disciplines, in particular health, where the investment is massive. And because it's multidisciplinary, so the science that you will be able to do is a science at the interface between disciplines. It's there where the innovation is still possible. The other one, colleagues, as in the case of photonics, the funding agencies, the bulk of the funding agencies made the nanosciences and nanotechnology as their priorities. If you apply these funding agencies with a project which is a nano, you are likely to have, how can I say, a funding. Aspect, colleagues, is the field where the funding from the government and the private sector is massive. And colleagues, here is the funding by a country within the years. Of course, you get that the US is the, how can I say, is the driving for research, but following and other countries, Europe, Japan, Russia, and so on. And we are somehow here at the bottom, but we are 0 degree Kelvin. There is an investment from countries from the south. And this is, colleagues, these are millions of US dollars. It's massive, colleagues. It's massive. So therefore, we in the R&D sector, we are always looking for funding, and therefore here is it. And colleagues, this, as I mentioned, you may think that from Africa and the global south, excluding China, we are low. No, colleagues, because this, colleagues, if you take values here and you consider the GDP, then the configuration is a little bit changed in a way that this is the outputs of in nanotechnology publications by GDP of the country. And as you can see, colleagues, the USA is not the top. One is Iran. And this clearly that in effect the rate of publication Iran is not spending the budget of the US in the field of nano. But when you divide these publications by GDP of the country, Iran is number one. And it's sustainable, colleagues. And the same thing goes up to 2022. And when you can see, colleagues, that Africa is not absent. It's not a African continent close to Italy, colleagues, and with a low GDP in science and technology, but extremely robust in terms of productivity. And Tunisia is a number 4, I think, or 5, or 6, sorry, 6. So Africa is there, South Africa is there, Egypt, Algeria, Cameroon, Nigeria, and so on. So it just shows you, colleagues, that we are not absent. We are not at the top, yes. A baby has to crawl first, walk and run, and Kipchoge, not will be world record breakers, but it is. And how can I say, colleagues, allow me just to go to now to the science. I was just hinting for how can I say, messages to the policymakers and to also those who are not in the field of hard sciences to understand why we should embark in nano. That does not mean it's the unique discipline, no, because as in the case of photonics, it's multidisciplinary and there is a massive funding there. So if we we're looking for jobs, this is the field where we have to go in. And if we have to innovate and to make, how can I say, to become a world-class scientist, this is a field where you have. And if you combine photonics and material science, so that is nanophotonics, done, you have done it. Colleagues, the name of the word of nano was coined by Norio Tariguchi, Japanese. He was the first one who mentioned the name, who used the name of nano. Nano means dwarf, small, okay? And it was a theoretician who predicted that in the year of 20,000, we should have reached the level whereby we would be able to manipulate atom by atom and to make an engine and to build a system atom by atom. And that was Ray Chapman. All of us who have done little bit physics went through his lectures. And in effect, this nano, it was not new. The Romans were using, how can I say, glass, colored glass. And this colored glass would change in color depending on the concentration of the material that they are mixing with the glass. Here, for example, it's a glass containing gold nanoparticles. They were not aware that they are forming nanoparticles of gold, but here they were mixing nanoparticles of gold with the glass to give it that color. At such a size, the gold is not yellow, but red. And this is just a plasmonic response. This is the interaction of the gold nanoparticles inside with its light. It's red. And here it gives you the green because it's, can I say, smaller sizes. Here it's a bigger sizes and here smaller sizes of the gold. And those who were making these glasses during the Roman Empire, they were not making nanoparticles. They're mixing salts in the glass. But they were making nanoparticles, and their response in terms of plasmonic response, it gives different colors. In effect, colleagues, and due to limitation of time, I will not go through it. In effect, colleagues, nano has not waited humanity to make it. Magnetostatic bacteria do produce, do bioengineer nanoparticles of iron oxide plots here. And as you know, the bacteria is the first living species. Yeah? And these magnetostatic bacteria, they produce these plots here, And these small plots, it's a pity that I should have increased the size, but the copy of the presentation will be present with the organizers. What is sure is that these are small plots and they form like a necklace. Why they form like a necklace? They orient these nanoparticles here are magnetic, and they orient themselves according to the magnetic field of the Earth. So just colleagues, just to mention to you that the nano is not a modern stuff, but it is, how can I say, it dates as early as fire, and certainly far before, million years before, within the magnetostatic bacteria. What is critical in the field of nanomaterials? If you take a material, imagine that you have a small grain, a spherical grain, gold, for example, or take whatever, but take gold, it's a metallic. The atoms on the surface do not have the symmetry. The atoms here inside are surrounded in the cubic system, the highest crystallographic symmetry. It is surrounded by 6 atoms inside. So it's the 3D symmetry. But if you take the atoms on the surface, they do not see atoms, how can I say, 4 atoms surrounding them. Because 3D symmetry is broken. And if it is the case, these atoms on the surface will vibrate differently. And therefore, the Raman, the infrared response will be different. And we do understand that the number of atoms on the surface will be very high sometimes relatively to the atoms who are inside. Smaller is the size of this particle, higher is the number of atoms on the surface, and if you go to a chemical reaction where the atoms of the surface are the major driving forces, you would see that the nanomaterials are extremely very active, very, very active relatively to the bulk, because the number of atoms on the surface is higher than the number of atoms inside. So the surface over the volume can be higher than 50%. The other thing, colleagues, is that when you have a charge inside free electrons, remember that we are in the case of nanoparticles of gold, so the electrons here, they are confined in a quantum well. Okay, it's in a quantum well. Therefore, it's not like in the bulk where they can travel from there to there easily. No. Here the electrons are confined in this space. And when they are confined, it's a quantum well. And you remember when you have done, how can I say, quantum mechanics, you started with this, how can I say, with this potential barrier, something like this, that is a quantum well. Therefore, what does it mean? This electron here, which is inside, will not behave as a particle, but it will behave like a wave. Therefore, its properties are governed by quantum mechanics. And colleagues, what happens is that the energy levels of this free electron will be quantized. You do remember, please, the potential well, unidimensional one, when you have done basic quantum mechanics. That's exactly what is happening here. So you see quantum mechanical temperature with the nanomaterials. So the size does indeed play a major role. The other thing is the surface. The surface to the volume. If you remember, we said, colleagues, in the case of nanoparticles, the atoms on the surface are the atoms who do control the interaction with light, interaction with the external stimuli in general, and the interaction with the gases or whatever. And here, colleagues, so the surface, which is extremely important, in the field of nanosciences and nanotechnologies. Imagine you take a cube, colleagues. Imagine you take a cube of platinum, because the platinum is extremely expensive. Or take a gold, Danny, pop. Take gold, we know it's expensive. You take a cube of gold, in the nano, what we do, we will cut this in half. If we cut it in half, colleagues, we will create two other surfaces, isn't it? Colleagues, are you following me? We create two new surfaces. Now imagine I take that one and I cut it also, the half. I will create other surfaces, and the same I do. But now I will cut not like this, I will cut like that, I will cut in this direction, and I will cut in this direction. So I'll get these cubes. Okay? So you do understand that now the amount of surface that I will have is not 1, 2, 3, 4, and 5, and 6. It will be this. Sorry. It will be a huge amount of small cubes, small particles, and these particles, their surface is massive. And that is why, how can I say, when we buy the car, otherwise, if the car industry would have to use bulk platinum in your exhaust, the car will be so expensive that you cannot buy it. Not everybody can afford it. But because of the amount of platinum in the exhaust, remember what they do in the exhaust? You are obliged to put a carbon which would decompose the CO2 to carbon and to oxygen, and which decomposes to less harmful gases. And for that you use platinum in the exhaust. And if I had to start my career, I would do science, but I will go to the exhaust and I will collect all the master the collection of the platinum. I will become rich in day one. Yet indeed that platinum is small, but it's worth of collecting. And how can I say, in Kenya you have before the most okay. Anyway, the importance, colleagues, is the surface, which is extremely important. Just remember this, colleagues, just to get it right. If you take 1 kilogram of particles, if you take particles of a 1 millimeter cube volume, imagine you take small cubes, 1 millimeter, 1 millimeter, take a cube of these particles, it has the same surface than 1 milligram of the same material, but with the cubes of 1 nanometer cube. If you to use an exhaust, this material in exhaust as a car manufacturer, you gram of platinum or gold in the exhaust. It's a nonsense. You will be using you will be taking nanoparticles of a gold of a 1 nanometer cube in size, and for such you will use only 1 milligram. So it will be cost. So you do see that small particles do have high surface to volume, which can be extremely very cost effective when it comes to application in technologies. The same thing, colleagues, if you remember, we said that electrons here in a bulk, they are governed by classical physics, and therefore the gold is yellow. But an electron, there is also light interaction with the electrons of the yellow. But when you have instead a bar of gold, you have particles, the electrons which are there, they behave and they are governed by quantum mechanics. They are wave particle, and therefore Heisenberg uncertainty applies, and therefore their energy levels are quantized, and therefore the response to depend on size and will depend on their shape. As you can see, gold can be yellow to orange to red, blue to gray, green. You may say, who is the most expensive? Is that? Of course, it's this. And this has a huge application in the medical field, in treatment, in of agents such as anthrax and so on. So, as you can see, you can tune the color of the gold particles by shape, by size or shape. So, and each of them has its own application. And you can see clearly, colleagues, this change of colors, it's in effect purely plasmonic response. It's the interaction between the electrons, the free electrons, which like act as a plasma, and the probe light. Of course, silver is yellow, colleagues, if you remember. Silver is yellow, but silver stops to be yellow, and you can tune its color like for a gold, because the silver can have, due to its crystal, can give you particles. This, how can I say, trapezoidal graph, you can generate different type of plasmonic excitation, longitudinal, transversal, and basal, and so on. So the message to be taken, colleagues, from here is that the optical properties of nanomaterials can be tuned by the topic law of condensed matter. So these are particles of gold. As you can see, this is the melting temperature versus the size of the particle. You can see, colleagues, that in the case of gold particles, larger is the diameter, higher is the melting temperature, lower is the size, lower is the thermal temperature. It can for very small particles of gold, they can melt at room temperature. You know? So, and the law related to the melting temperature versus the size is more or less derived by thermodynamic consideration, considering the size. You can see clearly that macroscopic parameters such as melting temperature is size dependent. And this work by Buffon in Switzerland from ETH was one of the first ones to confirm this size dependence. Something else, if it was not nano, you will not be able to buy a cell phone. No way. It will be so expensive that then you will be using the traditional phone to phone. No, with the bakelite even. Then you have, all of us, we have cell phones because we have contract, what, because it's cheap. It's cheap. Why is cheap? Because the red colors, the colors that you have on your laptop or on your cell phone, they are not rare earth. If they were rare earth, you will pay a very huge amount for your cell phones. And not everybody will have a cell phone. Know what's up. Okay, so here, how can I say? Because our cell phones, they use ZNS, zinc sulfides, with nanoparticles to generate at different sizes, would generate different colors. Why, colleagues? Because when you have a free electron a free electron within a box with a nanoparticle, a particle which its size is smaller than 100 nanometer, levels are quantized. If they are quantized, that means, how can I say, you will be able to generate specific radiation, specific absorption, and specific emission. And in semiconductors, if you remember semiconductor, one of its fingerprints, it's the band gap. Colleagues, you remember? Yes. But here, in the semiconductors, smaller is the size for the same element, smaller is the size, larger is the band gap. So the band gap is not a fixed property or characteristic of a semiconductor. No, we learned in the, just forget one. Here, colleagues, in the semiconductors in particular, the band gap is size dependent. Smaller is the size, larger is the band gap. So smaller is the size, difference are the the fluorescence of your material. In the case of ZNS, zinc sulfide, colleagues, the particles which are small, they are blue. When the big ones, when you they emit in the red and orange and so on. So you can see clearly, colleagues, here you have the same material, but you tune its band gap, and therefore you tune its optical response, its optical luminescence, which is not the case in if we have to use macroscopic materials. If we use macroscopic rare earth, if I want to have red, I will be using europium doped materials. If I want to have blue, I will use lutetium, what. But here, no, we have the same material, but which how can I say? But at different sizes, and it can be excited. How can I say? And emit different radiations. So the band gap is a size dependent. In addition to that, colleagues, in addition to that, if you take a crystal, remember its shape is governed by crystallographic symmetry. In the case of nanomaterials, the surface plate imposes the structure, the crystallographic structure. And the zinc oxide, for example, colleagues, you find it as a bulk like this, but at the nano you can find it at a nano belt, at the nano spring, at the nano highly oriented nano rods, a nano ring, a nano sword, name it. You can control the shape as much as you wish, and each of them is specific for specific application. So colleagues, they see that in effect, by opposite to the bulk, it is possible to control the shape. And this shape is extremely important, Well, you have also heard about meta structures, and all of done electromagnetism. We have been told the dielectric constant and the magnetic permittivity are positive. They cannot be negative. No, that's wrong. Not for. Because all parameters that are, how can I say, that physically are used are always in Maxwell equations, are always the ratio of the dielectric constant over the permittivity or the product. And there was a gentleman, Russian, whose name is Veselacho. He said, well, as much as the dielectric constant and the magnetic permittivity would have the same sign, so the product of the ratio will be positive, and therefore we are not violating electrodynamic. He was right, and he said therefore there must exist materials which have a negative dielectric constant or a negative magnetic permittivity, and the first one what we call metamaterials. And it happened that the first metamaterial which was observed is by John Pendry. By John Pendry, now continuous one, and he was the first one to demonstrate what we call superlensing. If you remember, when we have done this experiment of optics, geometrical optics, we have a slab of a glass, and we have a laser beam. We have always seen refracted beam is always in this direction, in this plane, not in this plane. when we have the incident beam like this. This is my normal to the slab, and with the refraction, it does not go this way. It always goes that side, isn't it? But for the metamaterial, it's the opposite. If it is in this direction, you can have a super resolution. And as we believe what we see, that is John Andrew who has done. I'm sorry, the image is not, it does not show very well. Is it possible to switch off that light, please? This. If possible, otherwise it's okay. It's okay, we can turn it. Maybe we just rotate the lamp. I take medicine and it makes my eyes very sensitive. Thank you so much, very kind from you. I really do apologize. So, colleagues, well, here is the term of it's a word nano, using a super lensing of metamaterial. As you can see, colleagues, it's a pity that you cannot see it clearly, but it's a highly the resolution of this. The image of a nano using this metamaterial slab is has higher resolution than the optical ones, and it tells you what we call super resolution that can be reached with these metamaterials. Anyway, and size-wise, colleagues, size-wise, Richard Feynman in 1960, he made this citation. He said that if we would be able to write at the nanoscale, we will be able to write the citation for the Lord citation on the top of a pin of a needle. If we were able to write, can I say, we'll be able to write the Lord Prayer on the top of a needle. Just to give you an idea how small is the nano. You can write all that text there on that one, if you will be able to write at the nanoscale, of course. And the field nanomaterials, you can find them in different shapes and different forms. As I mentioned last time, you can find them in a form of independent nanoparticles, as the one that the tube of dentifrice that you use, and you can find them in a form of a composite or as a thin films. Thin films, they are, how can I say, they can be large in this direction, but their size in this direction. And you can find them in a form or nano less than 100. It is a nanomaterial. For example, the nanotubes can be very long, but their basal dimension is less than 100. Therefore, it is a nanometer. And this is when you do electron microscopy, colleagues, this is what you can see here. The zinc nanobelts are extremely very long, but their dimension is less than 100 nanometer. The same thing for this multi-layered coating for optics. They can be extremely very long direction, but in this direction, their size is less than 100 nanometer. Now, colleagues, nano is not a revolution, but just an evolution. Early in the 70s, colleagues, we have had the coal industry. Then in the 50s, we have had the nuclear era. In the 60s, we have had the semiconductor era. In the 70s, we have had the biotech era. And in the 80s, we have the ICT and the nanotech. And from 2000, we started to have a combination of this and that is machine learning, artificial intelligence, and so on and so on. You would certainly, how can I say? So you can see, colleagues, that the nano is not an innovation, but just an evolution of the system. And the ones who pushed for it, it's not a government, no, it's not the business sector, no, it is you and me, because we wanted to store Netflix movies, our USBs. We want to store a huge amount of music and YouTube stuff on our USBs. And well, the storage capacity was just shrinking in terms of size. Before, when I was a student, I was using, and certainly my colleagues here, quite a number of them, they were using this disk here, which was nearly 20 or 30 centimeter over 30 centimeter and a millimeter in thickness. This is the IBM disks that we were using in our time to store a text. And the text, you cannot store even an MP3 song in it. But we were really proud that, oh, damn, yes, we can store. And now you move it from this disk here to a, how can I say, a smaller USB, which is a terabyte. We move it from this to that. How it comes that here the size is small and the capacity of storage is high? Here you cannot put a song, MP3, and here you can thousands of songs. You can put a number of movies. No, impossible. And the colleagues, why is that? Because in this case, information that the 0 or the 1 was stored on a size of a millimeter. Then, millimeter over millimeter. Then the size diminished about a micron. That is in these TV disks. And now we are, how can I say, able to store that information as 0 and 1 over a dimension of 1 nanometer over 1 nanometer. So you do understand that smaller is the area where you can store the information, the 0 or the 1, higher is the capacity of storage. And that explains why. And here, colleagues, we were able to do it because materials at the nanoscale were capable of shape at the nanoscale, colleagues. So it is you and need for the boost of nano. The examples that I would like colleagues to share with you are, I singled out some of them just to show you that in effect we operate within the full electromagnetism spectrum. I will start, I think, on gamma rays, ultraviolet, infrared, and how can I say? The first one, which is a purely fundamental interest, but it happened that the master student who worked on it, she became managing director of the research activities of the sole nuclear reactor in South Africa. This is Noluthando Tsangasikana. Colleagues, she has been able to confine mercury. She was able to bioengineer nanoparticles of mercury at room temperature. Mercury, is it liquid or solid? Colleagues, liquid, huh? Is it liquid? Yes. It's the unique liquid which is metal at room temperature. Now mercury has it evaporates easily. You do not see it if you have a mercury, but irradiate with the UV, you would see a vapor. And that vapor is extremely toxic. That vapor of mercury or mercury in water, when it comes to a body, it will methylate. And once it methylates, it will not come out. You will suffer. And in particular, in the case of fishery, when the mercury from the traditional mining, it goes to a water system, the small fish will, how can I say, will absorb it. And once it absorbs it, it will go through their system, internal system, and it methylates and it binds, and it will not come out. The big fish will eat it, and we at the chain will eat it. So that if we eat contaminated fish with mercury, we are in serious troubles. And it is the case for a number of countries, unfortunately. In particular, countries where they use traditional gold mining in Latin America, in particular in the east of, west of Africa specifically. So the idea is, and is, if you want just to have an idea what is the damage that can be caused by mercury, go and Google Minamata. Just Google Minamata and you will see, colleagues, the damage that mercury can create. And her idea is, I need to come with a solution whereby I can store this mercury and I will make it not liquid, but I will. How? Well, you can make mercury solid. You can make mercury solid in different ways. Mercury is unique material. Mercury is high density. Colleagues, he is just putting himself in a danger, this man. Certainly he passed away. May his soul stays in peace. We'll find in his body mercury. Anyway, it has a high density. That's extremely important. And it has a high substantiation. And also it's liquid, but it has, because it's liquid, it has it's smooth. So it was used as a mirror for infrared astronomy, as well also for inertial experiments, early ones. And mathematics was the first where quantum proven. It was the first time where, how can I say, the Dirac and the Schrödinger equation allowed us to know exactly why mercury is liquid at temperature. It's surrounded by thallium, I think, and gold. It's the first time where quantum mechanics has been proven correct experimentally, in particular. I will not go through why is that, but if you are interested, there is a paper. Go and Google it, and you will find it. The point is that because limitation of time, I'm obliged to do it. Colleagues, you can make mercury solid in different ways. The one, the crazy, and the if you take the expensive one, you have to take 2 diamonds and you squeeze mercury inside and you apply huge pressure, and that will be so huge that mercury becomes solid. The other way, this is expensive, not everybody has a diamond, not me. And the other way, take a tube of mercury, and I will with the mercury, I will, how can I say, and hopefully what I will have, the mercury at the bottom of the tube will feel the density of the mercury on the top of it. It will be so heavy so that the bottom will be solid. Okay, and the pressure at the bottom will be so high that, how can I say, due to this column of mercury, and that mercury at the bottom will be solid. And if I send an X-ray beam, I will see the fraction pattern. Well, when you do that, colleagues, you will find out that the pressure here, to have a mercury solid, it has to be around Pascal. And that the pressure of 1 gigapascal here corresponds to rho GH. It corresponds to a height of 10,000 kilometers. That if you want to have a mercury with this experiment that you can make to confirm that mercury is is solid here, you have to have a tube which is as high as the Annapurna in the Himalaya. This is a nonsense. You can't do that experiment. So how can I do it? So you have to go back to the, how can I say? You have to go back to the phase diagram and you say, the phase diagram tells me that if mercury at that temperature, I am in liquid in this, this is, and this is temperature. If I apply a pressure above this level here, nearly 1 gigapascal, the mercury will move from liquid to crystalline, okay? And if I go above, it will. The point is not to go to high pressures. Just here, we want to move from this at room temperature, from the liquidus to the solidus here, and therefore to have the rhomboid. I need to apply a pressure of 1 gigapascal. And colleagues, all of us, we have surface tension, and Laplace equations tells me that delta P is equal to that, and if I put delta P equal to 1 gigapascal, I would have a phi, yes, I would have a phi of the order of 3 nanometers, or around 3 nanometers. Anyway, colleagues, I will not go through the details. So I need to synthesize nanoparticles of mercury. If I do that, I will be able to have tension, and therefore the mercury will be solid. I will not go through all the details, but here is what she has done. She has synthesized particles of mercury, and there are quite different sizes, but there are small ones, and these are the small ones that they are now. As you can see, colleagues, when she synthesized the small particles, you can see clearly that spherical, mainly amorphous or liquid. But when you have centered, faceted configuration, that means it's solid. X-rays that nanomercury or mercury at the nanoscale is solid, and it's not liquid, and therefore the higher targets of storing mercury was right. Colleagues, I'll just move on this. If you remember, we have spoken about nanofluids, and sorry, colleagues, just in this case, to verify this solidification, we were X-rays range in this electromagnetic spectrum. And colleagues, if you remember, we have spoken about the nanofluids. I would like just to share with you that we can make the nanofluids by gamma rays also. That is really the bottom frontier of the electromagnetic spectrum. I'll go through, you know what is a nanofluid, hopefully, as we said. Now we can make them not also by laser ablation, but by gamma rays, and we call this phenomena radiolysis. So by irradiating, colleagues, let's say silver solution, silver precursor in water or in any other fluid, which can produce ROS, we can indeed have a radiolysis, and we can form nuclei, and from this nuclei we can have particles, and the phenomena related to radiolysis are well established. And colleagues, this is also showing clearly that in effect the thermoconductivity, as in the case of laser ablation, the thermoconductivity increases with the dose here in this case, and in effect there is a threshold dose of the gamma rays which allows me to reach a higher, and therefore it goes down. And allow me please, dear chair, just to share this last example. Here is liquid lensing. You see how use nanosystems to produce liquid lenses, but these lenses are their focus view is how can I say is tunable. Is that how can I use the properties of a leaf? You have noticed if you see some alloys here or early in the morning, you have the droplet of water on sometimes this water covers completely the leaf, but sometimes no, it does not. It's hydrophobic. Therefore, the water and hydrophobic. Why is that? Because the surface of that leaf has nano spikes, and these nano spikes make the surface super hydrophobic. So the idea is to do this, to create a material which has these spikes like this, and be able to manipulate and a lens. Here, for example, colleagues, the idea is bottom here we have a material which is with like an antenna, and here non-activated the hydrophobic, super hydrophobic, the hydrophilic, it wets the surface. And the idea is to tune this hydrophobicity, to move from this hydrophobic to hydrophilic to hydrophobic, so on and so on, using UV radiation. And if we do so, colleagues, that how can I say? What does it mean, colleagues? That means that this can be used as a tunable lens with a tunable focus. Yes, correct. So the focus of this liquid lens is not the same, and therefore you can tune the focus of this liquid lens. And for such colleagues, I don't go through the details and so on. What is sure is that the result initially is hydrophobic, and when we irradiate with the UV, with the time, the droplets, the wetting moves from hydrophobic to hydrophilic. So the contact angle changes, and therefore the focus of this liquid changes. And colleagues, this one, how can I say, the change of the focus versus the radius, and the radius of this lens can be tuned via UV. What's the phenomena behind it? I have no time. I will move, colleagues. We'll go to the last us. Colleagues, I will just to express our gratitude to this gentleman and to the institute idea that he has, how can I say, said in our brains. And this is the late Abdul Salam, to whom we are really, how can I say, there are no words in the Arabs or in the Laghous to express our gratitude to him and to the institution that he represents and the fellows that you have the opportunity to interact. And I thank you.
Thanks, Professor Malik Maza, for a nice motivation to adopt career and research in nanoscience and nanotechnology. So, floor is now open for the questions. If you have some queries.
For the case of the tunable lens, are factors such as the gravity focal application of that lens?
Well, can I respond? Yeah. That the change of focus is not gravity induced, is UV activated. That that liquid droplet is, how can I say, is supported by picked oxide nanorods. And these, at the top of them, it's always the nanorod, it ends only with the specific coordination, plus or oxygen minus. And what you do is that you activate these surfaces, the top surface of these nanorods with the UV, and you change their, how can I say, their indirectly electric polarity. And it's that one which controls the weighting of the droplet. It makes, remember, water molecules have a dipole, and therefore it is dipole of the polarity of the zinc oxide, the top, which makes which activates and makes that surface hydrophobic or hydrophilic. Either it repels the water molecules, the dipoles, or it attracts them, so making the angle and therefore changing the focus of. Thank you.
Great. Any other question? If no, I have like just a small question. Like this U2 AC N2, is like vision, is it like to build capacity and create awareness regarding nanoscience and nanotechnology, or is it like building a human resource for real incubations or some job market in nanotechnology in Africa? What exactly is the scope?
Yes, thanks a lot, Program Director. In fact, initially, of course, as I mentioned, the baby roll first, walk second, and run after. The initial idea of the UNESCO chair was to train as much as possible of fellows at the MSc and PhD level in the fields of nanotechnology from different disciplines and generate quality knowledge. And we said that by 2020 we should have been reached quite a robust capacity in that regard, and therefore in 2023 we should embark in innovation, R&D translation. And in that regard, now we are shifting our focus. We continue with the human capital development and so on. We continue with the training and creating more or less or duplicating somehow the same idea in different parts of the continent, but we are shifting towards R&D and to have fellows with an entrepreneurship mind. That is why our activities at ICTP, we would definitely duplicate them down in South Africa and in other parts of the continent. But you are right, we are shifting our focus not only knowledge generation and diploma and have expertise and so on, but also to be able to innovate. Why not to have an Elon Musk among us here? Excuse me, of course. Huh? I'm no Elon Musk, huh? But you guys, you can.
Nice. So just one small question. So are there some real incubations from Africa now, because it is like 2023 and beyond, and there are job market available in industry, like graduates coming in Africa now? Is it like reached to that level?
No, not yet. What is sure is that fellows have started to patent. At least you have a Moroccan and her husband having an IP on nanofluids, and because that an IP that they got a job in the US, and the other one got a job in how can I say, in Europe, but they started to and a fellow and his wife from Tunisia, they also IP O2 and to nanofertilizers. there is definitely a shift, as I mentioned, and for the moment, the level of creating companies, because it requires capabilities and so on, but rather patent and how can I say, license. And a fellow from Iran and South Africa came with a fantastic idea of designing and engineering a nanomaterial for cloud seeding. If you remember, colleagues, you have seen that in the news that there was a huge amount of rain in Dubai. Dubai does use a huge amount of cloud seeding indeed. And these fellows, can I say, came with the idea whereby synthesizing nanoparticles of cloud for cloud seeding in a cost-effective way, and it is less harmful than the methodology used in Dubai. So, but at least just to tell you that these now fellows here it's towards patent. But well, after the patent, certainly there will be a possibility to, hopefully, we will.
Yes, great. One last advice
Sure.
I would like to have from your side. So in terms of this nanoscience and nanotechnology, it's pure hardware based and technology based. So let's say if you compare something coming from developing world, you develop something where there is unavailability of raw material and processes and all that stuff, and then you compare the tech giants, big developers. So in the hard, it's always very hard to compete developed world. So what will be your comment in terms of nanoscience and developing something in this in the developing countries, how they are going to compete?
I think what is sure in terms of SDGs, we should not see it in the traditional way as a competition, but rather as a complementarity. You have a component which has financial resources, you have a knowledge, others have a possibility of manufacturing. So I think the way to go, the new way to go is to cooperate. Is to cooperate and make it real to ensure that we have a production.
Thanks,
Thanks
Professor
a lot.
Malik. There is one more question.
Yeah, thank you. Just looking at Google, I'm looking at your Google Scholar account, and maybe something that has drawn my attention is the citations. I think you have over 30,000 citations, and with a high H index. Maybe, and looking at the nature publications, your advice to, especially the professors who are here, and also the researchers, in terms of how you can keep the focus on research with the many distractions now going on, especially in the minds of young researchers. How can they achieve, especially what you have achieved?
I think personal achievements are not really individual. Whatever I have shared with you, it's not my job, it's the job of, and I have not had the time to mention to you what, and have done, for example, it's out simple way, tech idea, focused and so on, and using complementarity between the University of Nairobi and ourselves, exchange fellows who come with something. And well, it happened, you have one in Nature Scientific Report as a first author. Yeah. So I think key message is that we have to cooperate. We have to cooperate in a spirit of complementarity, not competition. That's one. Because one, to be flexible, not because you are an expert in a field that you block yourself for others. Try, for example, in the case of photonics, I mean, it's medicine, chemistry, name it. I think one should be not to stay in his or her own kingdom, but to be open to new disciplines and cooperate extensively and avoid to depend but rather invest the human capital and cooperate with the colleagues from the north as well as the south. In the north, there are quite well advanced capabilities. We have to work, and all of us have, if we trigger our minds in that regard, certainly the productivity will be higher. I mean, Moses and Nancy do co-author the bulk of their papers. So Moses will end by having 12 publications that and they do work together. Moses does a job and Nancy does another part, and they finalize the manuscript or they finalize whatever, but they come with something where they co-author. And involving colleagues from the north is extremely important, because it's really an outstanding signature. If I receive, as editor-in-chief of Nano Horizons, when I receive papers between African and colleagues from MIT, I cannot just reject. Even if it's not in the field, I have to take them. This fellow is from MIT, and this fellow is from Kenya. This paper involves the people from ICTP. I know what the ICTP is. I know what is MIT is. So when I see the co-authorship of that kind, how can I say, as an editor, at least in my little domain of Nano Horizon, I react and I take time to read and send it to correct peer reviewers. It's really important to cooperate with our colleagues from the north. And our colleagues from the north have started to see it as a reciprocal cooperation, win-win situation. And by associating yourself also in that way, you are enhancing for more collaboration, and you are broadening your network, and therefore your credentials. When I was at a conference, I now whom I have to knock in Kenya. I would say, I know who are they. So for that conference, I invite that. That is the kind, or I suggest for nomination of X, Y, and Z, I will definitely nominate. And now I'm very well aware about the excellence, and that's the way that we have to go. What is sure is that we should not, we have to have a mind of a person who would create a job, not a person who would go for a job, to look for a job. We have to create it. We need to have an Elon Musk. We need to have Steve Jobs. See, we need that kind of persons. Please, as I told you, PayPal, I do not remember the names of these two engineers who have not patented, or they were interested by the local market. They have not seen the big picture, but that is the attitude. And I think this hands-on training that we got, at least, I am a student, I learn every day. I am interested to duplicate this stuff in South Africa. So therefore, these fellows, if you come in, when we were going to an event in South Africa, you would see the same fellows here said, what the hell, I was attended this in Nairobi. But we are interested to duplicate this in our place, because how can I say, we would like to have other fellows from southern part of Africa, Botswana, Namibia, Zimbabwe, Eswatini, and to benefit from this knowledge that you acquired, and also to ensure that this how can I say, experience that you got here, we will duplicate it in other parts of the African continent and the south. But what is sure, Prof, for the researchers, I think it's, indeed, teaching is their main duty. Fine, yes, it's correct. But research-wise, it's extremely important, and they have to opt for more opening, cooperating with their departments, and also other universities, sister universities in Nairobi in general, and the region, Uganda, Tanzania, and so, and also keep the interaction with the overseas. So quality research comes out, and therefore the international community are extremely sensitive. I must admit, the international community is not biased at all. And when you have quite significant H-index and citation, funding agencies, they see that factor. Before, who is the PII? This one, let us see his credential, her credentials. So it's really important, not only as a personal achievement, but as a reflection of, how can I say, what can be produced as good from that network that you have created. Thanks.
Okay, we are running out of time, and
Yes.
because of that, we will give the opportunity to one more question online. They are asking here, you can do some comment about nanophotovoltaic and what are the challenges of nanomaterial for storage?
Well, for the photovoltaics, for example, as I have mentioned, and we have discussed with Prof. David here, he recommended, we have identified an ID candidate in that regard. Photovoltaics have a weakness. The first one is that when they are exposed to solar radiations, they become hot. And when the temperature of a PV increases by 5 degrees Celsius, its efficiency of conversion decreases by 1.7% approximately. So if you want to have your PV effective and operating in excellent conditions, you need to cool. And the cooling currently is by water. You know that we have seen that the water has a low thermoconductivity, less than 1 watt per Kelvin. And therefore, a nanofluid can be an opportunity in that regard. That's one. The second problem of the PV is in sandy areas or kind of dirty areas. You have sand covering the surface or the dust, and you need to have a surface that cannot on which the dust cannot stick, because if you have a dust, you are not collecting all the radiation on, they are scattered back. A bulk of them are scattered back. So you need to have a surface which is, may keep the PV clean. And also, remember, in a number of countries, they are obliged to use water to clean. But the water, as you have seen last time, quite a number of African cities, so they would not use water for cleaning. They would but not cleaning. So it is necessary to come with have to reduce dust, but on to the question of our colleague.
Okay. Let's change the presentation.
I said to myself, oh, sorry, let me just remove this.
Humans have always been curious. Why is the world the way it is? How does the world work? The excitement of new ideas, passion, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics supports research excellence in physics and mathematics, and the nurturing of
evolution journey. Visit our website at museum.mmu.ac.ke. MMU Museum, where the past meets the future.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Welcome to Multimedia University of Kenya, a center of excellence in engineering, ICT, and business studies. This is the iMac Lab that offers editing skills and use of iMac computers with various video editing softwares such as Final Cut and many more. This is our engineering lab, where we conduct technical evaluation of hardware equipment and software troubleshooting and fixing every possible technical issues. This is our physics and chemistry lab, where most practicals happen, including tests on materials, and present research findings to scientists, ensuring safety and quality standards are met.
computer lab, also known as Korea lab. This is where computer classes take place and most of the computers are stored with internet.
This is our laser and optics lab, which deals with laser and optics, including transmitting and manipulating laser beams or any other forms of laser light. Welcome to our radio. We have our own radio station that provides information to the citizens and people at Gatarongai. Listen to the sweetness of our radio on 99.9 FM and learn more from our students as they bring to you hot shows. This radio has greatly helped students acquire communication skills in readiness to join national and international radio stations.
A laptop is an essential asset in the modern society. However, many of them are lost as a result of theft taking with them vital information. But now comes Electracker, an online system that gives users the ability to register various electronic devices using their serial numbers. To access Electracker services, visit the website, create an account, log into your account, register the device serial number. In case your device is stolen, you report in the portal. Electracker will then help you track and recover the device.
I had lost my laptop, but thanks to Electracker, I found it. Asante sana Electracker.
Electracker helped me track and recover my lost laptop, which was stolen away from school. Wewe pia jaribu Electracker, cause iko fiti.
Hello, my name is Patricia Mativo and I'm a student at the University of Oxford. But for my undergrad, I went to Multimedia University of Kenya, where I pursued my bachelor's degree in analytical chemistry.
Hi, my name is Wandera Kisimbiri and currently I'm studying a master's program in chemistry at the University of Gothenburg in Sweden with a scholarship from the Swedish government. My journey began here at the Department of Chemistry at the Multimedia University of Kenya, where I pursued a bachelor's program in industrial chemistry.
Hello there, my name is Ambatsa Vanessa Ijesa. I am a graduate student at Multimedia University of Kenya, taking Masters of Science in Analytical Chemistry. I'm also a scholar under the Stipendium Hungaricum Scholarship at the University of Pécs in Hungary. I am taking a Masters of Science in Chemistry, specializing in research.
The master is thanks to the family and the community around the department and faculty that made me who I am today, a transformational leader.
If you told me I would be where I am today, I would probably call you a bluff. Multimedia University of Kenya has been nothing but transformative.
Work with various UN agencies and the government. This is because I was not only taught to become a chemistry student, but also to become an all-round disciplined student where I was able to bring in solutions for our modern world challenges.
One notable thing about Multimedia University of Kenya is that it offers the resources for you to grow as a student.
And this is why I think it will be important for you to consider applying to the Department for either your undergrad or postgrad.
Whether you're considering an undergraduate or postgraduate studies in chemistry, I would strongly urge you to consider Multimedia University of Kenya, which will set your path to a fulfilling future with academic excellence. Join us today and embark on your own journey of growth and achievement.
Well, all the best as you do that. Thank you.
What we are having today is an ongoing training. It has been from Monday, going to be 5 days until Friday, and mainly what we are training people in is the installation of solar panels and every component that comes with installations from home. If anyone needs solar PV technologies, the panels, the batteries, the charge controllers, the inverters, and so forth. So from this training, the students that you are seeing in the back view are learning the very basics to begin with, from electricity, these components, what they entail, what are they going to look for when they go to purchase such items, or even before they purchase them, what do they need to consider from the place that they want to install them into. We are an avenue of creating opportunities for the youth that take part in this training, because now they'll go forth with the certifications they acquire. They will acquire licensing to be able to install these technologies as technicians.
This week we have a solar PV training, photovoltaics training. It has started from Monday, 30th of November, and it is going for 5 days. So it's ending on 4th of December. So basically, we are instilling skills on solar installations, designing, and sizing. We have about 17 participants. Most of them are students from Multimedia University of Kenya, and they are really interested to know more about green energy technologies and solar technologies. After this training, they will be now skilled solar technicians.
I'm a third year student in Multimedia, pursuing a bachelor's in renewable energy and technology. So this week we've been here in the T1, T2 training, which is a renewable energy research consortium. I'm going to be a participant. I'm here because I want to be impacting my knowledge, and at the end of this course, I'm able to be consulted according to solar PV installation. I expect to have knowledge of installing myself and even assembling and coming up with new ideas to impact the world in terms of concentrating on the renewable energy. The experience so far is very good. It's the third day, but I think I have gained more knowledge than I expected. Right now we are doing the hands-on, the practical unit. I think they are impacting very well because it's easier to understand when it comes to the practical more than the theoretic. And I think it is very beneficial for me so far.
The experience is good so far. At the end of this program, I expect to have gained more knowledge, to be able to understand how to install appliances, how to choose the correct appliances, how to deal with customers and their demands, The experience has been very inspiring, being that there are more female students than male students. It's actually so programs.
It has been a wonderful experience as been an intern for the past 1 year since the consortium was established, and it has been a continual educational and a learning process. When I see myself wearing an overall, when I see myself carrying a solar panel, when I see myself connecting a battery to power the loads, it has been a wonderful experience being part of the consortium. And next to it, we are proud and even more happy to have the first T1, T2 training, solar PV training in MMU. It has been a wonderful journey, and as you can see the growth, even having the first T1, T2 training, it has been a great milestone. It has been a wonderful reception, and the students getting to understand and to these trainings, mostly from MMU, any other institution, from any other company in the energy sector, they can come to obtain the skills that are in line with the trainings that are.
This week is a landmark for us because we are having the first T1 solar workshop, whereby we are focusing on our young youth, especially the science and engineering students. And so far, so good. We had a very good feedback, whereby we have a total of about young men and women who are joined us in this workshop. We expect them